Today we're going to continue with Chapter 9, talking about projectile motion, but this time we're going to talk about simultaneous motion. So we're going to have two objects, both going in motion, and we're going to go ahead and be able to see some of their relationships. So first example we have here is a Ford pickup truck traveling east at 40 miles an hour, and then a Volkswagen traveling north at 30 miles an hour. They're both heading in the same direction. The pickup is 5 miles from the intersection. The Volkswagen is 4 miles from the intersection. So the first thing I'm going to do here is I'm just going to go ahead and draw you a quick picture of what's going on. We have the pickup truck going east towards the intersection that they would meet. We're going 5 miles away. Then we have the Volkswagen that's 4 miles from the intersection again, seeing some vectors here. But again, they're 4 miles away, so they're really -4 as their distance to that zero, right? We go negative, we go positive, or negative left, negative down. So that's their distance from that intersection. So what we want to do here is find parametric equations that model the motion of the vehicles and then simulate the motion of the cars by simultaneously graphing the equations. Make sure to adjust the windows accordingly so that, and turn off the axes so we can actually see them in motion here. So we're going to go ahead and start with the pickup truck, and their horizontal distance and motion as we're going would be that they're -5 miles from that intersection, and they're going at a speed of 40 miles per hour. So again, T would be hours, and they're moving at a rate of 40 miles per hour. Their vertical distance, again, if we're looking from an aerial view, would be nothing because they're going straight east. The Volkswagen, on the other hand, the horizontal distance, the latitudinal distance would be 0 because they're going due north. And then the vertical distance would be, again, you're going -4 away, and you're going north at a speed of, 30 miles per hour, where, again, T is your time in hours. So here's our parametric equations where, again, this is the Volkswagen. There's the pickup. And if we want to see this in action, let's go ahead and graph this. Remember from yesterday, in order to graph parametrics, we got to first change the mode so that we are in parametric form. Now, one other thing we want to do here is, because it's simultaneous motion, and maybe you guys have seen this in the past when you were doing linear equations and linear systems where you would have to graph multiple things at the same time. Normally, it finishes a whole graph before it starts the next one. We want to do simultaneous graphing. So we got to go down and also turn on simultaneous graphing so that it graphs both equations at the same time. Okay. Now we go to our y equals. Our first one is, again, the pickup. So -5 plus 40t. For our vertical distance, we got nothing. We talked about, let's go ahead and turn this to the key so that we can see the actual truck in motion. And then we do the same thing for the second vehicle. So that's 0 for the horizontal and -4 plus 30t for the vertical. Again, let's go turn this on so we can see the actual cars in motion. Now, again, the window, we have to think about this. So the window, again, looking at our kind of rough sketch here, we know the X-min should be at least -5, so we'll go ahead and leave it at -10. X-max there is fine. Y-min, I think we're fine here. Now, let's go 0.01 again. The smaller you make it, the longer it will take to graph, but if you go too big, then the lines will just appear and you won't be able to actually see it. So we're going to graph for 6 seconds, plotting every 0.01 second. And then the last thing I want to do, because we are on the axes, to make it a little bit easier to see, let's go ahead and go to Format and turn off the axes. There we go. Hit graph, and let's see what we get. So we see those cars going really fast, and it looks like they might have even intersected at the same time, but it went pretty fast. So let's go ahead and go back to window. Still graphing. 6 seconds might have been a little bit too long. We'll hit on to shut that down. Go to window. Looks like we don't need to graph for more than 2 seconds maybe. And let's even go slower, 0.001. And let's see this again. And again, at any point, if you need to pause the graph, hit enter. Let's try it again. There we go. If you hit enter, it'll stop, and you can kind of see where you're at. So as these things are approaching, it looks like the blue may have crossed in front, so they don't actually intersect at the same time. Might have gone a little slow on the second one, but that's all right. We got a good visual of that. So that was the pickup truck going east, the Volkswagen going north. And from our viewpoint, it looked like they may have just passed each other pretty closely, but we're going to go ahead and solve and see if that was the case. Now, if we go and check out part B, find a formula for the distance between the cars as a function of time. So we did this in the past here. Remember, we have, what do we do? Blue for the pickup. So over here, this is the starting point of the pickup. So we have -5 plus 40t. That would be whatever x value we have, and then 0 for the y. And then for the Volkswagen down here, we would have 0 for the x, and then -4 plus 30t for the y. So if we're representing the distance between these two vehicles, as they approach, it's going to get shorter, right? And then we'll be able to figure out if there is any point where it would be at actually 0. And if it is at 0, then that means they would have intersected and actually collided. So what we're going to do here is we're going to do the distance formula. So the distance is square root of, and then we have our x value for the blue. So we got -5 plus 40t minus, we should put them in parentheses, minus the x value for the green, and then squared plus the y value for the blue minus the y value for the green. And again, squared. Simplify a little bit on the inside just to make it a little bit nicer to plug in. For -32, be careful of the negatives there. And then what we want to do here is we want to minimize this graph. So we want to go ahead and minimize this to see the distance between the cars, to see what the closest the cars would have gotten to each other. So if it's 0, again, that means they collided. But if it's not 0, then that was the closest they would have came to actually intersecting. Now, be aware here that when we're talking about this graph, we have the distance as a function of time. So we're going to use the rectangular graph, not parametric, because we have one graph here. We're going to go back to our calculator, and we're going to go to the mode, switch it back to function mode, because we are in rectangular form. And then for our y equals, we're going to do the square root of, parentheses, -5 plus 40, x, or t, close them squared, plus 4 minus 30, t, close it squared. That's good. So again, when we graph this, I took off the axes, I forget about that. Go back to format, make sure our axes are on. There we go. Might have to adjust our window. So again, it looks like we're pretty narrow here on the x. It came down and went back up. Let's go to window. Let's make our x min and x max -3 and 3. See if that helps. That looks good. We can go a bit smaller. Why not? There we go. Okay. So it's pretty clear here that the minimum is right here. We want to go second trace or second calculate, do a minimum. That's good. 0.5. That's good. Minimum's between there. Hit enter. And it looks like the minimum was 0.131. I'll go more. 0.128 seconds. And they got as close as 0.2 miles. So we have the minimum of 0.128 comma 0.2, where again our time is our independent and 0.2 is our distance. That's the dependent. So what does this mean? This means that at 0.128 seconds, or minutes, I'm sorry, because we were talking in minutes. I'm sorry, hours. We were in miles per hour, correct? Yep, miles per hour. So 0.128 hours from the time we started and they drove, they were 0.2 miles away from each other. So that was the closest they ever got to intersecting. So at 0.128 hours, they were 0.2 miles away. And if you want to convert that to minutes or seconds and feet, you can do so on your own. For number 4, we have a similar situation. Each spring, Harry the hare and Tom the tortoise challenge each other to a race. Harry knows that he can run faster than Tom. He boasts he can give him a 100-second head start. Tom crawls at a rate, so we'll do blue for Tom. Tom crawls at a rate of 0.4 yards per second, while Harry's running speed on a good day is 2.5 yards per second. Challenge Tom to a 50-yard race. So if we look for our equations, the first equations, let's go ahead and do Tom first. Tom's the easy one. So Tom's x horizontal speed is going to be 0.4. So that's the horizontal distance. Now this is a two-dimensional race, right? Because they're just running on a straight line, kind of like they're running on the x-axis. So his vertical distance is not going to change. So for Tom, that's his parametric equations. For Harry, he's got x equals 2.5 yards per second, but he is losing 100 yards to start, or 100 seconds to start. So the time he's losing is 100 seconds because he gave Tom a head start. The vertical distance over this race is, again, 0 for him because, again, they're just running on a two-dimensional plane. So if we go ahead and plug these in, again, for parametric, because that's what we're talking about here, we want simultaneous motion. We'll go Tom is 0.4t. Leave the rest. 0 for that. Harry is 2.5 t minus 100 with the 100-second head start. And then again, 0 for the vertical. So if we're thinking about this, let's check out the window. Time, he's giving him a 100-second head start. So the t max, we better include at least that 100 seconds. So we'll go maybe 150. And we'll graph every 5 seconds. And then we're talking about yards. So y min and max, we don't need to do much because it's along the x-axis. So we'll go -1 and +1 because everything's going to be, again, along the x-axis. If they're starting at 0 for the race, let's just make the x max. I don't know. How long do we think they're going to run? 25 yards? Let's give it a look. Graph. So there's the race. Whoop, Tom was the blue, Harry was the red. That went by pretty quick. So let's go ahead and change our x max and take a look here. So, they did a 50-yard race. I'm sorry. So our x max, we should probably make at least 50. You know what? Let's just make that the end line. Hit graph. There's Tom. There's Harry. Let's slow it down and go maybe every one step. And then let's take away those x-axes so that we can see it a little bit better. All right, I think this will be my final time around. Here we go. So we can pause it if you hit enter. So there's Tom. He just started. He's going at about 0.4 yards per second. He's got a 100-second head start. So once you see the red appear in here, that was the 100 seconds that came up. Harry's flying in. And it's a pretty close finish, but that was a good stop. It looks like Harry won. Now, we're going to answer that question later mathematically. But that was a good visual of the actual simulation. And if you want to see a photo finish slower than that, you can again adjust the the window and slow this one down even more. Okay, so that's part A. For part B, where are Tom and Harry 100 seconds into the race? Well, you can just do that algebraically if you'd like, where Tom would be 0.4 times 110 seconds. So Tom would be, what is that? 44 yards into the race. And then Harry would be 2.5 times 110 minus 100. So he would be 25 yards into the race. So 10 seconds after Harry actually starts, because he gave him the 100-yard or the 100-second start, he would still be trailing. But then it says, will Harry still win the race if he waits 100 seconds to start running? Well, we can do this if it's a 50-yard race. We would say Tom would be 0.4 T equals 50 seconds, because that's his finish for the horizontal distance. And then T would be 125 seconds. So this is how long it takes Tom to finish the race. Whereas Harry, if you set it equal to 50, because that's the distance it takes to finish, when we solve for that, you get T minus 100 equals 2. So T would give him 102 seconds. Or sorry, 100 and that's a 2.5, 20. So that would take him 120 seconds to finish the race. So yes, Harry would win. Okay. And then at the end there, basically you can say how far ahead was the winner? Well, the winner was right here. So at 120 seconds, he was 50 yards away from the start. So we could just go and say, well, where was Tom after 120 seconds? So 0.4 times 120, he was at 48 yards. So Tom was at 48 when Harry finished.